Hi class, welcome to lesson 50, our first lesson in unit 8, acids and bases. In this lesson, we will define Arrhenius acids and bases, identify the general properties of acids and bases, and determine the products of neutralization reactions. Make sure you take good notes. You can use guided notes provided in Google Classroom or take your own. Write down any questions you have and bring them to class so that we can discuss them. You will need a Regents Chemistry reference table to complete this lesson. Gather your materials and let's get started. Acids and bases are special solutions which fall under the category of electrolytes. Earlier, we learned that electrolytes are ionic compounds that separate into free-moving ions when dissolved in water. In addition to ionic compounds being electrolytes, acids and bases are electrolytes as well. They produce ions in solution. Looking here, you can see the consequence of being an electrolyte. So here you can see that we have electricity coming from a socket used to power the light bulb, but the circuit is not closed as the metal strips are not touching. In a non-electrolyte, there will be no electrical conductivity because the particles do not separate into charged ions. When the particles do separate into charged ions, the particles will be attracted to oppositely charged electrodes, allowing for the completion of the circuit. That means that electricity will be able to flow in a circular fashion. Strong electrolytes will have great electrical conductivity, as we can see here with this bright light bulb. And weak electrolytes, like some organic acids, like acetic acid, will be able to conduct electricity. But notice how the amount of electricity produced, as seen by the dimmer light bulb, is a consequence of only some of the particles forming charged pieces. The fundamental description of an acid or a base is called the Arrhenius definition of an acid or a base. An Arrhenius acid is described as any aqueous solution that produces H+, also known as hydronium ion, in solution. Here you can see we have hydrochloric acid. Hydrochloric acid is really important because notice how it's covalent. Covalent particles are particles that have no metals. And because they share electrons, most covalent particles are not electrolytes, but acids are the exception. So acids are electrolytes because some of their covalent particles separate into ions. So in hydrochloric acid, you can see the ion is sometimes written simply as H+, a hydrogen ion, or the ion can be shown how it interacts with water. So we'll just add the hydrogen ion to water, and we'll call it H3O+ or hydronium ion. If you forget the name hydronium, you can find it on reference table E, the polyatomic ions. Now, acids generally have a sour taste, so we can think about when we eat Sour Patch Kids or lemons, they are acidic. Acids can burn your skin, and they have a pH lower than 7. Acids also react with active metals to release hydrogen gas in a single replacement reaction. Remember from Unit 6, we learned that a single replacement reaction with an acid can happen if the metal is more active than the hydrogen. So here you can see hydrogen, which when it's an element, we show it as H2. And now since magnesium is more active according to reference table J, it will undergo a single replacement reaction, and hydrogen will be released as magnesium and chlorine will bond together to form a neutral compound. So notice that due to the charges, we need to have 2 chlorine for every 1 magnesium. The common acids are listed on reference table K, so their formulas and their names can be found here. The first 4 acids are strong acids, meaning they are strong electrolytes, and the last 2 acids are weak acids or weak electrolytes. It's just important to remember that all acids are covalent, yet they are electrolytes. They are the exception to the rule. Notice that all acid formulas can be written with the hydrogen in front. This is the way a physical chemist will write the formula, as a physical chemist explains chemistry as it relates to protons, neutrons, and electrons making chemical bonds. But organic chemists do not typically write the hydrogen in the front of the compound. So we have an organic acid is called acetic acid. It's also commonly known as vinegar, is very commonly written without the hydrogen in the front. Instead, organic acids end with the functional group COOH, meaning their formula ends in COOH. Now you should be able to define Arrhenius acids and describe their properties. Arrhenius spaces are aqueous solutions where hydroxide, OH- is the only negative ion in the aqueous solution. So here we have sodium hydroxide. The nice thing about Arrhenius bases is most of them are actually ionic. And since they're ionic, we expect them to be electrolytes, and they are electrolytes. But when we look again at this very common base, sodium hydroxide, you can see that the only negative ion produced is the negative hydroxide ion. Now, hydroxide is a polyatomic ion, and it can be found on reference table E. Some of the properties of bases is bases taste bitter or chalky. A lot of medicine is made out of bases, and so when you're a kid and you take medicine, it's often strongly flavored to hide that bitter taste. Bases feel slippery or soapy, and soap is actually a base, and they have a pH of greater than 7. Now, bases are found on reference table L. Notice that most bases end in hydroxide. Of course, ammonia is our exception. Now, one important tricky trap to avoid is not all formulas that end in an OH actually contain a hydroxide ion. That means not all formulas that end in an OH will indicate a base. So it's important to know that organic compounds, which are compounds that contain carbon and hydrogen, often end in OH, but they are not bases. So an organic compound that is neither an acid nor a base is an alcohol. So alcohols begin with carbon and they end in OH, but they are not acids and they are not bases. And as we touched on before, some organic acids actually end in COOH. That's the functional group or the three-dimensional shape of an organic compound that makes it an acid. And if you see a formula that starts with carbon and ends in OH, just know that it is never a base, and it might be an acid if the last four letters in the formula are COOH. Again, you can always check if it's an acid by looking on reference table K. So by now, you should be able to describe Arrhenius bases and their properties. The science word for base is also alkali. We try and contextualize the difference between an acid or a base. We can look here at this chart. So we begin knowing that acids and bases are aqueous solutions in water. And water is a covalent compound, and most covalent compounds do not conduct electricity, including pure distilled water does not conduct electricity. But every 1 out of 10 million water molecules separates into ions. It separates into a positive hydrogen ion and a negative hydroxide ion. But since water, HOH, has equal hydrogens as hydroxides, water is actually both an acid and a base. So it's equally acidic as it is basic, which explains why its pH is in the middle of the pH scale with a pH of 7. Now, when you look at an acid, remember when you combine acid and water together, you'll have more H plus or hydrogen ions than the other ions. So we have more hydrogen ions, which actually lowers our pH. We'll learn more about how pH works later. And it creates a situation where the only positive ions are the hydrogen or hydronium ions. Now, bases, when mixed with water, they will have more hydroxide ions, that OH minus. So again, when we mix them with water, you can see that the only negative ion in this combination is the negative OH, also called hydroxide. So when we want to compare the concentration of the different particles, we mean molarity when we're talking about a concentration of an aqueous solution, we can see that the concentration of a neutral solution like water has an equal amount of hydrogen, H3O, and hydroxide, OH. The acid here is pictured in red and the base is pictured in blue. So the neutral solution like water, these are equal. And if we shift to a lower pH and have an acid is the result of having more hydronium and less hydroxide. And if we shift in the other direction where we have a higher pH, then we're going to have less hydronium and more hydroxide. The final thing we'll want to do is discuss the neutralization reaction. So when an acid and a base react in a double replacement reaction, it can also be called a neutralization reaction. In this reaction, the acid and the base will always neutralize to form a salt, which is an ionic compound, and water. So in a double replacement reaction between an acid and a base, we're going to have the hydrogen from the acid combined with the hydroxide from the base to form water. Remember when we were balancing, we sometimes called water HOH. You can still do that here. And then the remaining ions will combine to form the ionic compound. So our positive ion is typically written first, so we'll write sodium and then chloride. The ionic compound must always form so the total charge of the new compound is 0. Let me show you how a couple more neutralization reactions happen. The remaining examples will be in the next video, video 50, part 2. This concludes lesson number 50 on acids and bases. Make sure you've taken good notes. Write down any questions you have, bring them to class. Ask them and we will work through them. Complete your homework on Google Classroom and put your Regents chemistry reference table and your non-graphing calculator back in your backpack so you are prepared for class. I hope to see you soon.